So we'll
All
start
right.
with Sebastien Lau, and he'll be presenting combining data-driven models and expert knowledge for personalized support to foster computational thinking skills.
Yep, and this is work done at the University of British Columbia with my co-authors Lallé Yalcin and Christina Conati. All right, so there's plenty of evidence that game design can be effective to teach computational thinking at a young age, like in the early K-12 education. So with computational thinking, or CT, being defined as the ability to formalize problems and the solution in a way that can be interpreted by a computer. And it is thought to be a very important skill nowadays because computers are pretty much everywhere in our lives, right? However, the environment that are currently used to teach those game design learning activities tend to be highly exploratory and open-ended in nature. And because of that, often there is no definition of what is the correct or efficient behaviors in these environments. And this makes it hard for students to quantify the success of their progress or even sometimes know what to do in the first place. It can be confused as well. And it is also widely acknowledged that teachers, K-12 teachers, often lack of training to teach CT because it's kind of a new concept. And it can be difficult for them to also support the students. So to alleviate those difficulties, our approach in this work is to see whether we can design data-driven adaptive support to help to facilitate interaction with those game design open-ended learning environments. And this is motivated by the fact that such data-driven support has been found to be quite effective in other open-ended learning environments. That I just show a few examples on this slide to learn about programming or science inquiry. But of course, the main challenge in all of those data-driven work is decide what behaviors should be leveraged from the data to drive the adaptive support. So to address this challenge, our solution is a framework called FUMA that we developed at UBC. So FUMA stands for Framework for User Modeling and Adaptation. And the goal of this framework is to learn from data what are the behaviors that can be conductive or detrimental to learning in an open-ended learning environment, and that's what I'm adapting to. And FUMA can also recognize these behaviors in real time and decide whether a student needs adaptive support at runtime. So we have extensively evaluated FUMA with different exploratory learning simulations, such as the one shown at the bottom of the screen, and also in different MOOCs. And we found that FUMA usually is effective at capturing behaviors that can be relevant for designing data-driven adaptive support. We also have evaluated, used FUMA to evaluate whether we can actually design and deliver adaptive hints during interaction with one of those simulations at the bottom. So in red, there's an example of hints. And we found that these hints can significantly improve the learning performance of students as compared to receiving no hints. So it's a very promising result. So in this work, our goal is to leverage FUMA and apply it to design data-driven support for game design learning activities. And as a testbed for this work, we used Unity City, which is an environment developed by Yumi Academy, which is a Vancouver-based company. And so Unity City is built, of course, on the popular Unity game engine, and it is used by Yumi Academy to teach computational thinking at schools and camps all around the Vancouver area. So this is what Unity City looks like. And so basically, as you can see on the video, it offers a very free-form way to interact with the interface and create small games. And students can simply drag and drop things into the interface and customize a game object as they want. And eventually creating small games like this one, for instance, while learning about computational thinking. So the goal of this work more specifically is to collect student log data during their interaction with Unity City while they design games, feed this data into FUMA so that FUMA can learn a student model with, in particular, to identify behaviors that are conductive or detrimental to learning. And then we also show how we can interpret and mine these behaviors to design adaptive support with the help of Yumi Academy teachers. So this is what I will talk about today. So a quick overview of the talk. So I will first describe the data set we collected to do this data-driven work. Then I will show how FUMA works and how we applied it to Unity City. And then I will discuss some results and conclude. So for the data set, we collected the log data from 130 students who attended 5 lesson summer camps in and around Vancouver, organized by Yumi Academy. So this was in 2019, before the pandemic, of course. So this was, the study was done in full ecological condition, meaning that the teachers will teach the material as they always do. We as researchers were not present in the classroom, and all we did is analyzing the log data afterward. So the rundown of each of those 5 lessons is as follows. First, the student will start by playing a game, and the teachers will invite them to reflect on specific aspects of the game that are related to the city skills they want to teach in the lesson. Then the teachers will go ahead and demonstrate some city skills in Unity City, and the student can mimic what the teacher is teaching. Then in green, there's a challenge phase in which the students are invited to create a small game with specific constraints, goals, and game objects. And of course, the idea for them is to leverage some of the new city skills they've been learning in the lesson. And after that, there's more playing of the games. So here for this work, we really focus on this green box here, the challenge phase. And analyze the log data collecting during the challenges. And we do that because this is during the challenge that students, well, first of all, are interacting on their own with Unity City, and also when they're expected to leverage and apply the city skills they've been learning so far. So this is the most interesting part of the interaction for data analysis. We also decided to look only at lesson 1 and 2 out of the 5 lessons. And so looking at the challenge 1 and 2 for each of these lessons. And this is because of feedback from the UMI Academy's teacher that learning the initial skills at this lesson 1 and 2 is the most important. And so we want to see whether we can actually build FIMA student models at these 2 lessons for these 2, the challenge 1 and challenge 2, so that we can have sufficient time to provide adaptive support to the students early on in the camp so they can learn the initial skills. So from the logged data collected from Unity City, we generated a bunch of actually 386 features that are meant to capture all the possible behaviors with the Unity City environment. And those behaviors are of three types of behaviors. So first is behaviors related to the overall levels of activity of the students, such as how many actions they perform, their action frequency, and things like that, to show how engaged they were in the material. Then we generated features over tuples that are made of unique combination of action and game objects. So here is an example, for instance, on this little animation. An example of tuple is rotating a ground object. So here the action is rotating and the object is ground. It's a green rectangle. And so for all of those tuples that are available in Unity City, we collected features such as the frequency of usage of this tuple, its duration, longest repetition, and things like that. It's all described in the paper. And finally, we collected features relating to posing during the challenge. So all of those features were inspired by our previous work with FIMA, where we found that those behaviors are useful to capture the learning performance of the student, and also are easy to interpret. All right, so now applying FIMA to Unity City. So FIMA comes in 2 phases. So the first one is a training phase. And so first, the idea is to generate all of the features I just described in the previous slide. And then those features are fed into a clustering algorithm that is meant to group together students who behave similarly with Unity City. And then within each of the cluster, we mine association rules to identify what are the salient behaviors in each of the clusters. So just to show you what it looks like, here in yellow, it's an example of an association rule we found with FIMA, which captures behaviors related to the frequency of performing some tuple action, like rescaling the ball or rescaling the ground. So this is the type of behaviors we can mine with FIMA. And so at the end of the day, those clusters and rules provide us with a student model that captures the salient interaction or behavioral pattern with Unity City. And we can also retrospectively interpret those clusters and rules and check how well they relate to learning. And I will talk a bit more about that during the evaluation. And so the second phase of FIMA is called the classification phase, and it is meant to be used in real time during interaction with learning environments such as Unity City to provide adaptive support. So the idea from this is to generate the same set of features I defined before on the data accumulated so far. Then FIMA runs an online classifiers that is meant to assign students to the relevant clusters among all of the clusters that were learned in the previous phase, depending on the student behavior. And then FIMA also use the association rules triggered or satisfied by the students to decide whether this student needs adaptive support during the interaction. depending on the behavior that are captured in the rules. So this is the high-level gist of how FUMA works. And so for training FUMA, so for each of the two challenges from the lesson 1 and 2, FUMA was trained in tenfold nested cross-validation over students, and we use inner loops, the nested loops to function the FUMA's hyperparameters. So I won't give too much details here, but you can refer to the paper to learn more about these parts. Also, we compare the FUMA classifiers against a majority class baseline and random forest and SVM trained in a similar way, just for the sake of comparison. All right, so now I will describe results pertaining to each of the components of FUMA, namely the clustering, the classifier, and the association rules to drive adaptive support. So I will start with the clustering. So FUMA identified two clusters of students in both challenges. So the number of clusters is one of the hyperparameters in FUMA. So again, this is more described in the paper how this number is chosen. So what we did is we compare those two clusters in terms of the completion time of the students in each cluster. So the time they took to submit a solution to the challenge, and the completion success, whether they were actually successful in completing the challenge given the restriction and the constraints provided by the teachers. And so we show these two metrics on these slides. So the completion time on the left and success on the right. So what we found is that we have one cluster in orange that we label as low performing or LP because students in this cluster were significantly slower at submitting a solution, and the success rate was also significantly lower than the students in the green cluster, which we label as high performing or HP. So what this shows essentially is that just from the student behavior, FUMA was able to learn a cluster of students that actually relate well to capture well different levels of learning performance, which is what we want, so it's good. Now looking at the classification part. So here we want to see whether FUMA is able to assign new unseen students, namely now test set, to the relevant cluster, so LP or HP, based on their behaviors. So this we show the accuracy of the FUMA and the baseline classifiers on this chart. So on the left is challenge 1, on the right is challenge 2. So on the x-axis, you see there is first the accuracy, all is the overall accuracy over all students, and then we show the class accuracy for the HP and LP clusters respectively. So I will describe this result in step by step. So first, if you look at the red targets, we found that in terms of overall accuracy, FUMA and random forest are the two best classifiers, and they both significantly outperform both the SVM and the baseline classifiers. So it shows that those two clusters, FUMA in blue and random forest in orange, seems to be the best. But then when we look at class accuracy, those two classifiers behave a bit differently. So for random forest, it's actually better at identifying the HP cluster, as shown by the class accuracy for the HP, if you look at the red targets. Whereas on the other hand, FUMA is more accurate at identifying the LP, so low performing cluster. And this actually is pretty interesting because typically those low performing students are the ones who may benefit the most from adaptive support. And so it's actually great that FUMA can identify them. All right, and so the third part of the analysis is related to the association rules. So as I mentioned before, those rules are used to actually drive adaptive support with FUMA. So it's important that they actually make sense. So what we did is we conducted interviews with two experienced teachers and curriculum developers at Uni Academy. And we asked them to, in this interview, the goal was to assess the interpretability and the validity of the rules and making sure that they actually make sense and that the behaviors captured by the rules can actually sound and can be used to deliver adaptive support. And so we did so in particular, so the whole interview methodology is described in the paper, but in particular, we wanted to assess whether teachers agreed with FUMA or whether the behaviors captured in the rule are actually HP or LP behaviors. Of course, we will not show to the teachers the FUMA label, so there is no bias there. We will just show all of the rules in a random orders to both teachers separately. And so what we found, for instance, is on this chart, so we have the y-axis is the total number of association rules learned by FUMA across challenge 1 and challenge 2. And on the x-axis, we have for the two teachers, whether the number of rules for which they agree with FUMA, disagreed with FUMA, or could not interpret them. So some of the interesting results here is first that there's quite a strong agreement between the two teachers and FUMA. As you can see, it's for almost 80% of the rules. And so this is good because it shows that the behavior learned by FUMA and the labels, HP and LP, actually makes sense. And the teachers are able to recognize them easily and during our interview. There's little disagreement, which I will actually discuss in the next slides. And finally, there is a few rules for that one teacher could not interpret, but the other teacher felt he could interpret them easily. So it's interesting that there's a bit of mismatch, but overall, the number of non-interpretable rules seems to be minimal. So that's also showing that the rules learned by FUMA tends to be fairly interpretable. Now, the next part of the interview was to assess whether the behaviors captured by the rules are actually informative enough and useful to deliver adaptive support in the eyes of the teachers. And so we did that by asking them whether they will intervene in the classroom if they were to observe the behaviors captured by each of the FUMA rules and how they will intervene. So in this talk, I just focus on the LP, so the low performing rules, but in the paper, we also describe for the HP rules. So we found actually three main threads in those rules so far that I will share. So first, there were several rules in the LP cluster that were related to having a sparse or infrequent interaction with game objects, different game objects. So both teachers agree that this is a problematic behavior because students are supposed to be more proactive in exploring the material at hand. And it's actually the goal of open-ended exploratory environments. And they also acknowledge that it's sometimes not always easy to spot this type of sparse interaction early in the classroom. So they found it's actually great that FUMA can actually recognize those behaviors and quantify them automatically. They both agree that this warrants giving adaptive support to the student, and they mentioned that usually in the classroom, this means that the student is not really sure what to do or how to move forward, they're a bit stuck. And so typically what the teachers will do is invite them to reflect on the goal of the challenge, try to make them think about what they can do to solve it or actually to move forward. And if it's not enough, they will escalate into suggesting them to perform an action or a few actions to get them starting, and usually they can pick it up from there. The second thread is relating to performing a quick action after deleting a game object. So both teachers agree that it can be a panic reaction after deleting something by mistake. And they mentioned that they actually observe that quite frequently in the classroom. It's very frequent behaviors. And usually when this happens, they try to show the student how they can remediate to their errors by showing them, for instance, how they can cancel the previous action, going back in the history of actions. And it's actually a very important skill to acquire to be able to identify errors and coming back. And thirdly, FUMA found a bunch of rules relating to performing optional actions late in the challenge. So optional here being defined as an action that is not required to complete the challenge, but that can just make the game more fun or more advanced. So interestingly, FUMA found that these behaviors are low performing, perhaps because the actions are optional or maybe because they come late in the challenge. So FUMA thought these students are being slow. But both teachers strongly disagree that this is a low-performing behavior. They both felt that this is okay, that it shows that the students are still engaged with the material and are still trying to discover new things, even if it's late in the challenge or not optional. It's perfectly fine in their view. So it's quite interesting here, and it shows that there might be, capturing those, labeling those behaviors might be a bit more tricky, and it might be interesting to see how we can do that in FUMA to classify those behaviors more like in a more positive way. So these are some of the results we found. So to conclude, so I showed how we can apply FUMA to Unity-City in this talk. We discussed how FUMA can identify behaviors that are detrimental or conducive to learning with Unity-City, which is an environment that leverage game design to foster computational thinking. We discussed how Unity-City can actually detect and monitor these behaviors in real time and identify them and use them so that FUMA can deliver adaptive support to the students at runtime. And we also conducted interviews with the teachers to assess that the rules are interpretable enough and that they make sense and they can be used to actually drive adaptive support during the classroom. And as a matter of fact, what we are currently working on right now is implementing and testing some of the adaptive data-driven support we discussed in this talk by using FUMA in real time in conjunction with Unity-City and by collaborating with the UMI Academy's teachers to design the pedagogical content of the help. And so some of the things we are trying to pilot test or explore right now are shown on this screen, where we have a little pedagogical agent that will pop up and give some hints to the students based on the behaviors captured by FUMA. So I would be happy to discuss more of this kind of ongoing work later on after the talk. But in the meantime, thanks for watching.